Do you feel like buying a shovel and digging a 20-foot hole with a 10-foot radius, then placing 675 venomous snakes you just caught in the deepest parts of Australia, then throwing your math textbook into your pit of snakes? Terrific. We can help you avoid getting fined $25,000 for keeping exotic animals by watching this here video by Fort Bend Tutoring and Mr. Witt.
Hello ladies and gentlemen, this is Mr. Witt with Fort Bend Tutoring, and today's tutorial is going to be about finding the X and the Y intercepts of a rational function. That's what we're here for. Alright, so we have our rational function form right here. That's going to be anytime you have a function f of x that equals to a function divided by another function, all right, especially when our q of x, that denominator there, does not equal to 0, because you can't have 0 in the denominator of a fraction. You can't have 0 in the denominator of a fraction. All right, so you would then end up with parent functions that look like this. All right, so one parent function for a rational function is 1 over x, and its graph looks like this. Yeah. Or you can have a parent function for a rational function that is 1 over x squared, and it looks like this. Okay, so that's just to give you an idea of the rational functions that you may see from time to time. And what we're going to be doing in this video is trying to find where these rational functions intersect with the x-axis or with the y-axis. Notice how there is a vertical asymptote, all right, where the graph will not touch, as well as a horizontal asymptote where your function will not touch either. So in this case, you wouldn't have an x-intercept or a y-intercept, but they're all not going to look like this. Okay, so let's go ahead and check out some rules that we can use in order to find the x and the y-intercepts. So for instance, if I'm trying to find the intercepts for any rational function, the first thing I want to do is be aware of the domain. See, knowing what the domain can and can't be is going to assist me in finding any extraneous solutions that I may find for my x-intercepts, for instance. Okay, so that's going to be important for you to find out. Be aware of the domain of the rational function. Secondly, in order to find the x-intercept, go ahead and set the numerator equal to 0 and solve for x. And then you'll want to check for extraneous solutions. In other words, you want to guarantee that that value of x is within your domain. In other words, what x can be. As far as your last step is concerned, finding the y-intercept, go ahead and just plug in 0 for x and solve for y. That's it. That's all you have to do. All right, I know you're excited, right? So let's go ahead and put this into practice. Let's check out some examples. Here we go. In our first example, let me go ahead and straighten that out. There we go. We have g of x equals x plus 5 divided by x minus 10. Now, we want to find out what the domain is first. So be aware of domain restrictions when it comes to rational functions. Well, you're dealing with a fraction, and you should know that you can't have 0 in the denominator of a fraction. All right, that makes it undefined. So as far as finding out what our domain is, all I have to do in this case is set the denominator not equal to 0. So we'll find that x minus 10 cannot equal to 0, and then when we solve for this, we'll find a domain that does not include 10. All right, so x can be any other real number, but it can't be 10. All right, so we'll keep up with that. And for those of you that are interested in interval notation, you can say that the domain is going to be from negative infinity to 10 union 10 to positive infinity. All right, there you go. Okay, so in interval notation, your domain looks like that. All right, so there you go. Try to get some extra work out of me today. I see how you're doing. I see what you're up to. Trying to make me work hard. The x-intercept, all you have to do, ladies and gentlemen, now that we know that x can be everything except for 10, in order to find the x-intercept, you take the numerator of your original rational function. All right, I'll show it for you real quick. There it is, that g of x equals to x plus 5 divided by x minus 10. You want to set the numerator equal to 0 and solve for it. Yeah, that's what you want to do. So let's set the numerator equal to 0 and solve for it. So I'll have x plus 5 equals 0. Solving for x, I'll be subtracting 5 to both sides of the equal sign there to find that x equals to negative 5. Now, this is my x-intercept, but as you should know by now, you'll want to write your x-intercept also as an ordered pair. Okay? Formalize that. So we'll rewrite it as, in an ordered pair, negative 5, 0. Yeah, and that's my x-intercept. Right there. That's all there is. It's over now. Now to find your y-intercept, all you'll need to do is plug in 0 for x in the original function and then solve for y. So replacing all of our x's with 0 in our original function g, we can rewrite it as 0 plus 5 divided by 0 minus 10. And this gives me 5 over negative 10, which you will simplify to rewrite it as negative 1/2. All right, so simplified, our y-intercept is negative 1/2, but as an ordered pair, we'll say that it is 0, negative 1/2. Just like that. Okay, that 2 is ugly, and I'm gonna fix it. I'm gonna fix the 2 because it was a, oh, that's a no. Let's see the parentheses. Better. There you go. See, that's prettier. Okay, so here you go. That's your y-intercept. There you have it. I'm gonna put red boxes around my answers because it pleases me. All right, so here we have the X-intercept. There we go. And we have the Y-intercept. There you go. All right, so we find that the X-intercept is at negative 5, 0, and the Y-intercept is at 0, negative 1/2. Let's go ahead and graph that now. All right, so we now have our original function here, g, and we know that we have an X-intercept at negative 5, 0, and we have a Y-intercept at 0, negative 1/2. All right, so let's go ahead and plot those on our Cartesian plane right here. So negative 5, 0 is going to give us a point right here on the x-axis, and our y-intercept is at 0, negative 1/2, so that's going to be about right there. Okay, so that's my x-intercept, and this is my y-intercept, and there we have it for that problem number 1. Let's move on to our next problem. Okay, we're here on problem number 2. Problem number 2, we have f of x equals to 1 divided by x plus 6. So we're going to find our domain now, okay? We want to be aware of the domain for extraneous solutions of the x-intercept, all right? We don't want to falsely say that we have an x-intercept when there really isn't one there. So I'll be setting the denominator not equal to 0 and solving for x in this case, okay? And we find that x cannot equal to negative 6, all right? Just like that. And for those of you that wanted interval notation, here you go. You have negative infinity to negative 6, union negative 6 to positive infinity. All right, so there's your domain written in interval notation. All right, so you get a bonus for watching this video. All right, check that out. Now to focus on the x-intercept. In order to find the x-intercept, you set the numerator equal to 0. So if I were to set the numerator equal to 0 here, I would get a false statement, wouldn't I? In fact, I don't even have the variable x in the numerator. That's one thing that'll just tell you right off the bat. There's no x-intercept for this function. You don't even have the variable x in there. And in fact, let's just be clear. If you don't have the variable x in the numerator of your rational function, you're not going to have an x-intercept. Nope. So for the x-intercept here, we're just going to simply say it's none. None. Yep. You don't have an x-intercept. None. It doesn't exist. Okay, so but for the y-intercept, all you have to do is plug in 0 for x and solve for y. So if I were to simplify that process, I'll say that I have 1 divided by 0 plus 6, and if I simplify that, I end up with 1/6 as a result. So remember, this is what y equals to. This is going to be f of x equals to this value. So as an ordered pair for the y-intercept, I can say that it's going to be 0, 1/6, and that's it. So boxing up my results here, I don't have any x-intercepts for this rational function, so there's going to be none. And then as far as my y-intercept is concerned, it's going to be at 0, 1/6. Just like that. All right, let's go ahead and graph that. So here we have our original function, f of x equals 1 divided by x plus 6, and the x-intercept here for this problem doesn't exist. So it's going to be none. I'm going to write none right here. There you go. None. Whereas the y-intercept we said is going to be at 0, 1/6. Yep, that's where we're going to have that at. So being as though I don't have to graph an x-intercept, I won't. But my y-intercept, where the function touches the y-axis, is going to occur at 0, 1/6, right above the 0 there. Yep, just like that. There you go. There's my graph. On to problem number 3. Here we have it. Coming your way. We have g of x equals x squared minus 9 divided by x plus 2. In order to find out what your domain is, and you want to find out what the domain is first, thank you, you're going to set the denominator not equal to 0. So x plus 2 cannot equal to 0. Nope. And so to solve for this, I will subtract 2 to both sides. I'll end up with x cannot equal negative 2, and then, for those of you that wanted interval notation, I can show that this is going to be from negative infinity. Oh, that is ugly. Fixing it. That's a little better. Negative infinity to negative 2, union negative 2 to positive infinity. That's an ugly 2. Oh, I'm going to leave it be. I'm going to leave it be. Anyway, that's that. That is your domain right there. It is your domain. Okay? All right. Let's continue here. Then the x-intercept. For your x-intercept, you'll be setting the numerator equal to 0 and solving for it. So we'll start off with x squared minus 9 equal to 0. But then we'll find, since we're dealing with a difference of squares, we can factor this. All right. So for those of you that needed help with factoring differences of squares, check out this video right here. Okay? Check that out. I'm in it. So you'll end up with x plus 3 times x minus 3 equals 0, and then using the zero factor property here, okay, what you can do is you can set each of these factors set equal to 0 and solve for each, right? So I'll have x plus 3 equals to 0, and I'll also have x minus 3 equals to 0. All right, and then I'll solve for each. So in the first one, I'm subtracting 3 to both sides to find out that x equals to negative 3, and I'm adding 3 to both sides in the second equation to find out that x equals to positive 3. That means I'll have 2 different points for my x-intercept. I have 2 x-intercepts. And as ordered pairs, these will be written as negative 3, 0, as well as 3, 0. So these 2 points are the x-intercepts for this rational function. Now, as far as the y-intercept is concerned, all you do is plug in 0 for x and solve for y. So that means that I'll be replacing the x in the original function with 0. So I'll have 0 squared minus 9 divided by 0 plus 2. Well, this gives me a result of negative 9 halves. So as an ordered pair, my y-intercept is going to be 0, negative 9 halves, and done. That's it. Oh, you don't like that negative sign? All right, that was better. Okay, so there you have it. So we now have our x-intercepts, which were 2 in this case, and we had 1 y-intercept for this rational function. Let's go ahead and box this up. That's right, gift wrap your solutions for your teacher. Gift wrap them. There you go. Now let's go ahead and plot these on our Cartesian plane. All right, so we have our original function g of x equals x squared minus 9 divided by x plus 2 with x-intercepts at negative 3, 0 as well as 3, 0. And we have a y-intercept that's at 0, negative 9 halves. And now plotting these on our Cartesian plane here. The first one's going to be at negative 3, 0, so I have a point right here. I'll have another x-intercept at 3, 0, and I'll also have a y-intercept at 0, negative 9 halves. Now, you may not know where negative 9 halves is, but if you were to convert this improper fraction into a mixed number, it would be negative 4.5. So that's going to give me a better idea of where that is. So the point 0, negative 4.5, is going to be about right there. All right. So here I'm showing my 2 x-intercepts as well as my y-intercept for the rational function. On to our next problem. Problem number 4 is right here. So check this out. We have a domain that we need to find first. So that means that we'll need to set the denominator not equal to 0. So I have x minus 4 cannot equal to 0. And if I were to add 4 to both sides, here, I end up with x cannot equal 4. Interval notation, you have negative infinity to 4 union 4 to positive infinity. That's my domain. I know that my value of x cannot equal 4. Now, as far as the x-intercept is concerned, that means I'll be setting the numerator equal to 0 and solving for it. So my numerator is 2x minus 8 equals 0. So if I were solving for x, I'd be adding 8 to both sides to get 2x equals 8, and then I'd be dividing both sides by 2. So this tells me that x equals 4. All right. So now that I see that x equals 4, I want to double check to make sure that's going to fall within my domain. But remember, the domain says that x cannot equal to 4. So that means I can't use this. Yeah. In other words, I won't have an x-intercept for this rational function. So the x-intercept for this problem is none. I won't have any because the value of x cannot equal to 4. Okay, as far as the y-intercept is concerned, however, you'll be replacing all the x's in the original problem with 0. So it becomes 2 times 0 minus 8 divided by 0 minus 4. This gives me negative 8 divided by negative 4, which is positive 2. So my y-intercept for this problem is going to be at the point 0, 2. So boxing up my answers, I have none, and I also have a y-intercept of 0, 2. So no x-intercept, but we do have a y-intercept. So let's go ahead and plot that. So once again, we have our function h of x equals 2x minus 8 divided by x minus 4. We do not have an x-intercept for this problem, but we do have a y-intercept at 0, 2. So plotting our y-intercept on our Cartesian plane here, we'll end up with a point at 0, 2, and that's going to be the graph for problem number 4. All right, so that concludes problem number 4. Let's check out our next part of the video. So I wanted to talk about what happens between vertical asymptotes. And you should know that when you're dealing with rational functions, there are times where the horizontal asymptote is 0, that in between the vertical asymptotes, you can end up with an x-intercept anyway. Well, let's say that the horizontal asymptote is y equals 0. Well, that's the x-axis. So normally the function would approach 0, but never touch 0. However, between the vertical asymptotes, you'll find in many cases that the rational function will still have an x-intercept between the vertical asymptotes. So be aware of that and look for that. So here I'm showing that you can still end up with an x-intercept here because it ends up with a parabola shape between the vertical asymptotes. And this graph also shows how you can still have an x-intercept here. So you should be aware that you can still have x-intercepts and y-intercepts between the vertical asymptotes even if the rest of the function avoids it. All right, so keep that in mind. All right, let's continue. Here we have our next example, which is example 5. So in this problem, you want to start out by finding your domain. All right, so always be aware of your domain so you can know what to exclude from your pool of choices, especially for your x-intercepts. So we'll take our denominator of x squared minus 6x plus 9 and set it not equal to 0 because you can't have 0 in the denominator of your fraction here, of your rational function. So factoring this, you'll have x minus 3 times x minus 3 cannot equal to 0. So since you have multiplicity here, in other words, you end up with the same repeated factor of x minus 3, we can just solve for one of those. So I'll have next x minus 3 cannot equal to 0, and I'll solve for this by adding 3 to both sides of my not equal to sign here, and I'll end up with x cannot equal to 3. All right, that's the domain. X can't equal to 3. And for those of you that love interval notation, I'll have it written this way. I'll have negative infinity to 3 union 3 to positive infinity. All right, so that's going to be the domain for this rational function. Knowing that, all we have to do now is set the numerator equal to 0 and solve for it. So that means I'll be taking that x squared plus x minus 12, setting that equal to 0, and then of course I'll use the zero factor property, and I'll factor this, set each factor equal to 0, and solve for it. So I have a factorization of this that's going to be x plus 4 times x minus 3 equal to 0. And then after setting each one of these factors equal to 0 and solving for it, you'll find that x equals to negative 4 and x equals to positive 3. And these are my potential x-intercepts. However, recall that our domain excludes the number 3. That means that this potential answer for our x-intercept, that x equals 3, is extraneous. We can't use it in the solution because it violates the domain. That means that our only x-intercept for this rational function is going to be at negative 4, 0. And that's it. So we just have one x-intercept, even though we ended up with 2 potential results for our x-intercept. Because the 3 was not a part of our domain, we had to exclude that as far as being an x-intercept, which is why it's important to be aware of your domain prior to finding out what the x-intercepts are. All right. Then as far as your y-intercept is concerned, all you have to do is plug in 0 for all the x's in the original function and solve for y. So this becomes y equals 0 squared plus 0 minus 12 divided by 0 squared minus 6 times 0 plus 9. Simplifying this, you'll end up with negative 12 ninths, which reduces to negative 4 thirds. So that means that our y-intercept will be at the point 0, negative 4 thirds, and that's going to be our y-intercept. So let's put some red boxes around these intercepts. So we have our x-intercept that's going to be at negative 4, 0, and we also have a y-intercept that's going to be at 0, negative 4 thirds. Let's go ahead and graph this. All right, we have our original function, f of x equals x squared plus x minus 12 divided by x squared minus 6x plus 9. And we have an x-intercept that'll be located at negative 4, 0. And we also have a y-intercept that's going to be at 0, negative 4 thirds. And we will be graphing both of these intercepts on our Cartesian plane right here. All right, so we'll start out with negative 4, 0, right? So from the origin, we'll move to the left, 1, 2, 3, 4, and I have a x-intercept right here, okay? And then I also have a y-intercept at 0, negative 4 thirds. So converting that into a mixed number, that's negative 1 and 1/3. So I know it's going to be a little bit below negative 1 on the y-axis. So right here at the origin, I move down 1 and then a little bit beyond that, and I have my point right here. And those are the intercepts of this rational function. And that concludes problem number 5. Let's move on to our next one. All right, so for problem number 6, we have y equals x plus 1 divided by x squared minus 16. So in order to find the domain, you want to start with that first. You're going to set the denominator not equal to 0. The denominator of the rational function cannot equal 0. So that being the case, I'll have x squared minus 16 cannot equal to 0. Then, because this is a difference of squares, I can factor it. So factoring, I'll end up with x plus 4 times x minus 4 cannot equal to 0. You'll then want to solve for both of these, okay? So set each one of these factors equal to 0 and solve for it. For instance, I can have x plus 4 cannot equal to 0. I can have x minus 4 cannot equal to 0. You like that? And then I'll be solving for each one of these. So I'll be subtracting 4 in the first equation here, and I'll have x cannot equal negative 4. And if I add 4 to both sides here in the second equation, we have x cannot equal positive 4. So these are the two exclusions for our domain. The domain can be any other value except for negative 4 and positive 4. And for those of you that are waiting on the interval notation of this, I'm going to put it up here. We'll say that it's going to be negative infinity to negative 4 union negative 4 to positive 4 union 4 to positive infinity. There you go. So this is the interval notation of your domain. You got it. All right. So your teacher will obviously let you know their preference. All right. So either interval notation, or you can set it up just like this and just tell them, hey, x is such that x cannot equal to negative 4 and positive 4. There you go. Knowing that, in order to find out where our x-intercept is, we simply set the numerator equal to 0 and solve for it. So I have x plus 1 equals to 0, and then I'll solve for that by subtracting 1 to both sides here. And I find that x equals to negative 1. So that means that as an ordered pair, our x-intercept is negative 1, 0. And that's our x-intercept. We know that this intercept is good because it doesn't violate our domain. The only values that were excluded from this problem was x equals negative 4 and x equals to positive 4. And since we end up with negative 1 as our value for the x-intercept, it's good. We're cool with that. All right. So now let's move on to finding the y-intercept. And what is it that we do? What is it that we need to do? Exactly. We need to plug in 0 for all the x's in the original problem and simplify it. That's all you need to do. You ought to be having fun with this process by now, right? So this simplifies to give us 1 over negative 16 or negative 1/16 as your value for y when you replace all the x's with 0. So our ordered pair for the y-intercept will be 0, negative 1/16. There you go. There's your x-intercept, there's your y-intercept, and done, son. So now I'll be placing a red box around my answers because that's how I get down. Red boxing it. You got it. Red boxing it. Your x-intercept and your y-intercept, let's graph it. Okay, all right. There you go. Line it up. Center it. Yes. No. Oh, Okay, good. Good. We found that our x-intercept is going to be at negative 1, 0. Oh, yes. And we found out that the y-intercept is going to be at 0, negative 1/16. Exactly. So let's go ahead and graph that on our Cartesian plane. The rectangular coordinate system, we have it right here. And the first point that we're going to be plotting is the x-intercept, which is at negative 1, 0. So from the origin, I move one place to the left. I have a nice dot right there. I have a point right there. That's my x-intercept. Okay, and then for the y-intercept, it's going to be at 0, negative 1/16. Now, negative 1/16 is going to be very close to the origin, right underneath it. So that's why I want to place my point for the y-intercept. So here I have it, right here. Okay, perfectly placed. Thank you very much. And that is going to be the graph of our x and y-intercept for our function here. So that was for the function y equals x plus 1 divided by x squared minus 16. Yeah. So now we're moving on to our next problem. All right. Here we have it. Problem number 7. We have f of x equals 5x divided by x squared plus 2x minus 8. The domain for this function, we'll need to set that not equal to 0 and solve for it. So here we'll have x squared plus 2x minus 8 cannot equal to 0. If I were to factor that trinomial, you'll have x plus 4 times x minus 2 cannot equal to 0. If I set each one of these factors not equal to 0, I would end up with the following result. I'll end up with x not equal to negative 4, and I'll also end up with x cannot equal to positive 2. So these solutions here describe my domain, that x cannot equal to negative 4 and x cannot equal to positive 2. In interval notation, I'll have negative infinity to negative 4 union negative 4 to positive 2 union 2 to positive infinity. And this, let me get in view. There you go. So this is the interval notation for our domain. As far as x-intercepts are concerned, you simply want to put the numerator here, that 5x, you want to set it equal to 0 and solve for it. So let's do just that. So for my x-intercept, I'll have 5x equals 0. I'll then solve for x by dividing both sides by 5 using that division principle of equality, and I'll end up with x equals 0. So that means that my x-intercept is at 0, 0. That's the ordered pair. There you go. Then, as far as the y-intercept is concerned, you simply replace all the x's with 0 and you simplify. So in this case, I'll know that y equals 5 times 0 divided by 0 squared plus 2 times 0 minus 8. All right, and then simplifying this, I'll end up with 0 divided by negative 8. And then simplifying that, I just get an answer of 0. Well, lo and behold, I should have known that because of this right here, that the origin is also going to be my y-intercept. Okay? And there you go. So as far as the process for finding out the x-intercept and the y-intercept is concerned, you can still show your work to verify that your y-intercept is the origin. So of course, when you're dealing with math, documentation is key, not just to solidify the process for yourself, but also because it's especially important for the reader to be able to understand how you came up with your answer. All right? So there you go. Let's go ahead and red box this. So I got a red box around my x-intercept and a red box around my y-intercept, which is the same point, by the way. All right, so let's go ahead and graph this. So here we are back with our original function, which is f of x equals 5x divided by x squared plus 2x minus 8. And we know the x-intercept is at the origin. That's right, 0, 0. Look at that happy, excited face right there. And yeah, there you go. Here's another. This one looks sadder though, doesn't it? Okay, this face, that face right there, it looks like I just woke up face, right? Whereas this face looks like a worried face. Interesting. So the differences in my zeros create a different look altogether. All right, well, anyway, it's the same point. And this point, the origin, is both the x-intercept and the y-intercept. It's where the graph touches the x-axis and where it touches the y-axis. So if I were to graph that, I would have a point right here at the origin. And done. And done. There you go. There's the graph for problem number 7. And that's going to conclude this video on rational functions. Okay? So there you go. So ladies and gentlemen, as always, please rate, comment, and subscribe. And if you're able, please donate, as that helps us bring you more free math tutorials from me, Mr. Witt, and Fort Bend Tutoring. Peace.
Thanks for watching. We feel great knowing that you got some help and you're safe and sound. Now, if you'd be so kind as to like this video, subscribe to our YouTube channel, Fort Bend Tutoring, and like us on Facebook, we'd be much obliged.